United States Central Command recently released unprecedented footage detailing Operation Epic Fury. This massive coordinated strike deep inside Iranian territory completely obliterated the supreme leadership compound, officially eliminating Ayatollah Ali Khamenei. The weapon delivering this historic regime ending verdict is a marvel of aerospace engineering, known globally as the Tomahawk land attack missile. We are going to break down the exact physical, aerodynamic, and computational mechanics guiding this weapon directly to its target in Tehran. The Tomahawk guarantees absolute destruction through extreme stealth, algorithmic precision, and devastating terminal ballistics. A Tomahawk begins its journey inside the vertical launch system of a destroyer or the torpedo tube of an attack submarine. The launch sequence initiates with the ignition of a solid propellant rocket booster, known as the Mark 106. This booster provides a massive, instantaneous thrust of roughly 70,000 pounds, violently ejecting the missile from its steel silo. Picture this launch phase as a miniaturized space shuttle liftoff, compressed into a 21-inch wide steel tube. The sheer G force subjects the internal components to immense stress. This requires heavily reinforced circuitry and solid state electronics. The booster burns for exactly 12 seconds. This brief violent acceleration pushes the missile clear of the launch platform and establishes the initial velocity required for sustained flight. Following booster exhaustion, pyrotechnic bolts sever the connection, jettisoning the spent rocket motor into the ocean below. Simultaneously, the tail fins unfold, providing aerodynamic stability. A fraction of a second later, the main wings deploy from the fuselage. Finally, the air inlet scoops open, feeding atmospheric oxygen into the Williams International turbofan engine. This turbofan engine represents a masterpiece of miniaturized propulsion. It operates by drawing air through a low pressure compressor. It forces a portion of this air into a high pressure combustion chamber and bypasses the remainder around the core. This bypass air provides the majority of the thrust while simultaneously cooling the engine casing. Cooling the casing proves crucial for minimizing the infrared thermal signature. Inside the combustion chamber, specialized JP-10 high-density jet fuel mixes with the compressed air and ignites. JP-10 packs an immense amount of chemical energy into a very small volume. It acts essentially like liquid dynamite, tailored for sustained combustion. The resulting expanding gases drive the turbine blade, sustaining the compressor cycle and generating continuous forward momentum. The missile settles into a subsonic cruising speed, moving at roughly 550 miles per hour or Mach 0.74. Flying below the speed of sound offers massive advantages in fuel efficiency and thermal management. Think of this cruising phase like driving a hybrid car on a perfectly flat highway at exactly 55 miles per hour. The engine sips fuel at an incredibly slow rate, maximizing the total distance traveled. A supersonic missile burns fuel voraciously, creating a massive heat trail visible to infrared satellites. The subsonic Tomahawk glides quietly. It manages its energy reserves with absolute perfection, granting it an operational range exceeding 1,000 miles. The aerodynamic profile of the Tomahawk contributes heavily to its long range lethality. The cylindrical fuselage reduces the radar cross section while lowering parasitic drag. The main wings feature a high aspect ratio, providing maximum lift with minimal induced drag. This wing design mimics the aerodynamic efficiency of a high performance glider surfing on invisible thermal currents. The skin of the missile utilizes specialized radar absorbent materials, soaking up incoming electromagnetic waves and converting them into microscopic amounts of heat. The engine air intake is buried along the underside of the fuselage, hiding the highly reflective spinning turbine blades from ground based radar systems. Managing the boundary layer of air flowing over the missile skin remains crucial for maintaining stability. The smooth, seamless construction restricts turbulent airflow, ensuring the missile slips through the atmosphere with the elegance of a hunting falcon. The fuel system incorporates complex baffles inside the tanks, halting the high density JP-10 fuel from sloshing during high G maneuvers, thereby preserving the center of gravity. Every single gram of weight is meticulously calculated, balancing the explosive payload against fuel capacity and electronic countermeasures. Navigating heavily defended enemy airspace requires a brain capable of processing millions of data points per second. The Tomahawk relies on an integrated suite of guidance systems, working in perfect concert to ensure pinpoint accuracy. The foundation of this system is the inertial navigation system, utilizing ring laser gyroscopes and accelerometers to track the missile's exact movement through three-dimensional space. To understand this system, imagine walking blindfolded through your own house. You rely on your internal sense of balance and your memory of how many steps you have taken to know your exact location in the hallway. The Tomahawk performs this exact task using quantum mechanics. The ring laser gyroscopes utilize the Sagnac effect to measure rotation with mind-bending precision. Two laser beams travel in opposite directions around a closed triangular path within a sealed cavity. As the missile rotates in flight, the path length for one beam increases while the path length for the opposing beam decreases. This microscopic discrepancy creates a shift in the interference pattern of the lasers, a shift measured by highly sensitive photodetectors. The flight computer translates this optical data into exact angular velocity, knowing precisely how far the missile has rolled, pitched, or yawed. The accelerometers complement this by measuring the physical push and pull of gravity and acceleration using microelectromechanical systems. Tiny masses suspended on microscopic silicon springs shift under the forces of acceleration, altering the electrical capacitance of the circuit. The computer reads these electrical changes, calculating the exact speed and distance traveled. The mathematical integration of these sensor readings occurs thousands of times per second. Over long distances, inertial systems accumulate microscopic deviations requiring external correction. The missile employs terrain contour matching, commonly known as TERCOM, to eliminate these variances. As the missile skims just meters above the Earth's surface, a downward pointing radar altimeter constantly measures the distance to the ground. The onboard computer compares this real-time elevation profile against a highly detailed three-dimensional topographical map stored in its memory banks. Consider a blind person reading Braille. They feel the physical bumps on the page to understand the text. The Tomahawk essentially reads the topographical bumps of mountains, valleys, and plains using its radar, matching the physical shapes to its digital map. When the radar profile matches the digital map, the missile confirms its exact latitude and longitude, feeding course corrections to the flight control surfaces. This terrain-hugging flight path keeps the missile hidden deep within the radar clutter of the ground, masking its approach behind natural geographical features. As the Tomahawk approaches the terminal phase of its flight, it activates the Digital Scene Matching Area Correlation System or DSMAC. A digital camera located in the nose cone snaps rapid-fire photographs of the terrain below. A sophisticated image recognition algorithm compares these high-contrast images against preloaded satellite photographs of the target area. This system operates identically to the facial recognition software on a modern smartphone. But instead of mapping the contours of a human face, it maps the intersections of roads, the corners of buildings, and the shapes of coastlines. The algorithm identifies these distinct visual features, verifying the target with absolute optical certainty. This system guarantees surgical precision, placing the warhead within a specific window of a specific building. Modern iterations of the Tomahawk integrate highly encrypted military-grade global positioning system receivers. The GPS system receives timing signals from multiple orbital satellites, triangulating the missile's position down to mere centimeters. The system incorporates advanced anti-jamming antennas, cutting through electronic warfare environments with brute force signal processing. The missile remains in constant communication with regional command centers via ultra-high frequency satellite communication links and the Link 16 tactical data network. This two-way data stream allows military commanders to monitor the missile's health, track its progress, and issue mid-flight retargeting commands. Assuming the primary target relocates or a higher priority target emerges, operators beam a new set of coordinates directly to the missile's flight computer. The missile instantly calculates a new trajectory, banking sharply to engage the updated objective. You can compare this capability to a driver receiving a real-time rerouting alert on a GPS navigation app due to a sudden traffic jam. The missile analyzes the new route and smoothly adjusts its heading. The ability to dynamically adapt to shifting battlefield conditions transforms the Tomahawk into an intelligent, loitering hunter-killer. The true terror of a modern cruise missile strike lies in the mathematical orchestration of the time-on-target protocol. Neutralizing a heavily fortified command compound requires an overwhelming synchronized impact. Firing 20 missiles sequentially allows the enemy air defense systems to identify, track, and intercept the incoming threats individually. The time on target algorithm ensures that all 20 missiles launched from entirely different geographical locations at different times detonate on the target at the exact same millisecond. Consider a scenario where 20 friends living in completely different parts of a massive city all agree to arrive at a specific restaurant table at exactly 7 o'clock in the evening. The person living furthest away must leave their house hours early, while the person living down the street can leave at 6:55. They must constantly check their speed, account for traffic lights, and sometimes take a longer route just to waste time and perfectly synchronize their arrival. The mission planning software performs this exact coordination for the missile swarm. It calculates the total flight time for the most distant missile and establishes that duration as the baseline. The launch sequence begins with the furthest platform firing its payload. Hours later, the closer platform launches its missiles. The flight computers on board each Tomahawk communicate with each other through the secure data link, constantly adjusting their speeds. The closer missiles deliberately throttle back their turbofan engines, trading speed for fuel conservation, allowing the distant missiles to catch up. Furthermore, the closer missiles fly complex, winding flight paths, deliberately extending their journey by executing pre-planned dogleg maneuvers and circular holding patterns. They wander through the airspace, intentionally expending time until the synchronization window aligns perfectly. The synchronization of the swarm relies on an incredibly robust and secure communications architecture. The missiles utilize frequency hopping spread spectrum technology, constantly shifting their transmission frequencies thousands of times per second. The network operates autonomously, with each missile acting as a node in a flying mesh network. Assuming one missile suffers a catastrophic failure or falls to anti aircraft fire, the remaining missiles instantly recalculate their timing and trajectories, dynamically reassigning targets to ensure all primary objectives receive the required explosive tonnage. As the final seconds tick down, every single missile converges on the target from a different compass heading. This 360-degree simultaneous convergence completely saturates the defensive capabilities of the target. Radar systems become overwhelmed by the sudden appearance of dozens of threats attacking simultaneously from every conceivable vector. Anti-aircraft batteries face a mathematically unsolvable problem, lacking the processing power and the physical ammunition to engage the entire swarm at once. The synchronization algorithms execute flawlessly, guaranteeing that the defensive grid collapses under the sheer volume of the incoming strike. The flight represents the culmination of this immense technological effort. The missile executes a final maneuver designed to maximize the destructive potential of its payload. Depending on the structural characteristics of the target, the flight computer selects a specific attack profile. For deeply buried bunkers or reinforced concrete structures, the missile performs a pop up maneuver. It pitches aggressively upward, climbing thousands of feet into the air before rolling over and diving in a steep, near vertical trajectory. This maneuver translates the forward momentum into immense kinetic energy, driving the hardened steel casing of the warhead deep into the target structure before detonation. For softer, above ground facilities, the missile maintains its terrain hugging altitude, slamming directly through the reinforced walls in a horizontal strike. The primary warhead, designated the WDU-36B, utilizes PBXN-107, a plastic bonded explosive representing the pinnacle of destructive chemistry. Older explosives possess extreme volatility, detonating from simple friction or moderate heat. PBXN-107, conversely, is incredibly stable. You could strike a block of this explosive with a steel sledgehammer or set it on fire with a blowtorch, and it will merely smolder. It requires a highly specific, massive electrical initiating shock from a specialized detonator to trigger the main charge. This extreme insensitivity ensures the missile survives the violent forces of the launch phase and the friction of atmospheric flight, entirely avoiding premature detonation. The explosive crystals are suspended in a polymer matrix, binding the energetic material together while providing a cushioning effect against accidental impacts. Upon target impact, the smart fuse sends an electrical current to the detonator, creating the precise initiating shock required to trigger the main charge. The fusing mechanism employs a programmable delay, ensuring the detonation occurs deep inside the heart of the building. The instant the fuse triggers, A chemical reaction propagates through the explosive material at a velocity of nearly 8,000 meters per second. The solid explosive instantly converts into a mass of superheated gas, expanding outward with unimaginable violence. This expansion creates a hypersonic shock wave, generating an overpressure wave measuring thousands of pounds per square inch. This phenomenon mimics a localized, instantaneous hurricane forged entirely of fire and kinetic force. As this primary shock wave expands outward, it reflects off the solid ground, merging with the original wave to create a vastly amplified front known as a Mach stem. This amplified shock wave pulverizes reinforced concrete, snaps structural steel girders like dry twigs, and completely liquefies any surrounding biological matter within the immediate blast radius. The initial positive pressure phase crushes the building inward, while the subsequent negative pressure vacuum violently tears the remaining structure apart from the inside out. The casing of the warhead shatters into tens of thousands of jagged steel fragments, riding the shock wave at supersonic speeds, shredding all surrounding materials. The thermal flash incinerates combustible materials, raising the localized temperature to several thousand degrees Celsius in a fraction of a millisecond. The destruction of the chosen target becomes an absolute physical inevitability. The target area transforms into a crater of pulverized debris, erased from the topographical map with surgical finality. The combination of subsonic stealth, algorithmic terrain masking, perfectly synchronized swarm tactics, and devastating explosive chemistry ensures total mission success. The target encounters absolute destruction, overwhelmed by a swarm that calculates, adapts, and executes its final directive with flawless mathematical precision.